Really nice to be here with you, everyone. And I'll be talking about two things today. I'll try to keep it within about 45 minutes. So MARRS is an application. It's a tool where you can simulate your stereo recording and immersive 3D recording. I know some of you are working on 3D recording, so I'll be introducing some research I've done over the years and some practical microphone techniques with some binaural audio samples. So firstly, start with MARRS, Microphone Array Recording and Reproduction Simulator. It's an app for helping sound engineers make correct decisions on placing microphones and configuring the spacing and the angle between the microphones. If you're a recording engineer, you've done location recording, then you know how difficult it is to find the best spot for your microphones and how to angle your microphones and determine the right amount of spacing between them. Me as a recording engineer myself, I've always wanted to make correct decisions, in my stereo recording, because I often found that, if your microphone spacing is too large, then you always have this hole in the middle and exaggerated stereo with nothing in the middle. It's like everything is just super wide. But sometimes if you narrow your microphone angles, then you end up with very narrow images. And also one of the things I see in education, in recording sound recording, teaching sound recording in general, there is a lot of like preset-based teaching. So, okay, if you use ORTF, it sounds like this, and if you use XY, whatever degrees, and yeah, this is it. And or if you want to have a wide spatial sound, then you should have a AB, spaced omnis, whatever. But this is like just teaching, like feeding people with some like a foods, rather than teaching how to catch your fish. You basically feed them fish. But maybe they can survive with a couple of different types of foods for a while, but then if you run out of it, then you don't know how to survive anymore yourself. And in recording as well, a lot of sound recording engineers, they just go with experiences, and and then if they find some nice technique that works for them, then they just stick with it. But that kind of limits the creativity and the adaptability. If you go into a new venue and then the acoustics totally new and your ensemble layout is totally different, then you cannot use the same technique anymore. You have to be able to adjust your microphone configuration according to your situation. So that was my motivation, and actually this app was developed in 2017 or 16, but the underlying principles are based on my PhD. Actually, it was actually my first experiment in PhD in 2002, and at that time I didn't really know the values of my own result. But then after 10 years or so, and then I started thinking, why did I not think about this? I can actually use this to make an app, right? Because it's a very like a it's an algorithm that is very straightforward but very accurate psychoacoustically. So I decided to make an app, and that was the beginning. And then it turned out to be a very useful tool for teaching recording, but also for critical listening training as well. So you can actually hear all the differences between different techniques binaurally as well. Yeah, so that was a long introduction, but I'll show you some screenshots. You can download this app from Google Store or Apple App Store. It's a free app. So basically, you can see this virtual stage with all these virtual sound sources and your microphone array. And in this view, you can see where each of these objects will appear between two speakers in stereo. You can customize your setting by changing spacing, angle, and so on, polar patterns and that. Actually, one of the unique things about this app, compared to other similar tools like Image Assistant or If you're familiar with Michael Williams' great works from the 80s, 90s, yeah, there are similar apps available, but this tool basically visualizes all the objects and the microphone array as well. And you can also simulate the height of the microphone as well, and also the vertical tilting angle. So it gives you more realistic simulation environment. And this is the MARRS for the web, which I'll demonstrate a bit later on. This is a web version where you can easily access and play with these 4 sources. It's limited to 4 only at the moment, but we plan to expand it for more sources in the future. And you can also play the audio binaurally. You can turn it on and off. So if you're using loudspeakers, you need to turn it off. But I'll play binaural samples today because everyone is wearing headphones. That's great. Yeah. So a bit of principles for this app. Yeah, this was the experiment I've done in 2002, but the actual paper was published in 2013 in the AES journal. So it was a paper by me and Ramsey. So we looked into the independent effect of interchannel time difference and interchannel level difference on the perceived image shift for 2-channel stereo. So we were using 60-degree speaker angles, and so this ICTD shift factor can be modeled this way. It's don't worry about these numbers yet, but just looking at these plots. So if you want to shift your image by 10 degrees from the center to the left or right, then you basically need to apply about 0.25 millisecond time difference. And if you look at the median values here, for 20 degrees, it's about 0.5 millisecond, double the value that you need for 10 degrees, right? But then for 30 degrees, the value is basically doubled from this point. So it needs about 1 millisecond. So you can draw a straight line up to there, and then you can also make a straight line there. Of course, there are other angles in between those 2 points, but if you look at the error bars basically indicate the uncertainty of localization. So different people will perceive it in different positions slightly. And this error bar becomes larger and larger as the angle increases, which is natural result because our localization ability is not as good in the lateral region as in the frontal region. So based on this psychoacoustic result, you can make a very simple equation like this. So it's a region-based shift factor, as opposed to previous models that used some complex regression, nonlinear relationship. So I basically make this simple shift factor up to 20 degrees, and from 20 to 30 degrees you can just make it doubled. Similar relationship for the level difference. So you need about 4 dB, 4.25 dB for 10 degrees, and then 8 to something dB for 20, and then you need about 17 dB for 30 degrees. So we have the similar relationship here. So this was the basis for the psychoacoustic model I came up with. But if you're interested more about the details, you can go to this paper and find out the actual method that we used. And yeah, so now I'll talk about MARRS model, which was introduced in this paper, Intelligent and Interactive Tool for Microarray Design. From those two, the independent level and time difference results, I came up with this linear time and level trade-off functions. So this basically shows how you can combine level and time differences to achieve certain degree of image shift. So in the previous plot, we saw that if you want to shift the image by 20 degrees, you need either 8.5 dB or 0.5 millisecond. But if you combine these two values somewhere on this line, so for example, if you have 4.25 dB combined with 0.25 millisecond, you can also achieve the same image shift. But of course, the perceived spatial characteristics will change. This is what you can hear using the MARRS app as well. But yeah, if you use just the time difference, then it gives you very spacious sound, but localizability will decrease. It will be more difficult to pinpoint where the source is. Whereas if you use a level difference, then you can pinpoint the image, but the sound will be very narrow. I mean, probably you're all familiar with it. So OLTF, like near constant array, uses both level and time differences. So it will be somewhere along this line. Yeah. So maybe if you're familiar with the precedence effect, we know that if you have 1 millisecond time delay, then you have the sound image perceived at one direction, the direction of the earlier sound, regardless of the level difference. So beyond 1 millisecond, you will always hear it from the earlier speaker. Similar thing happens with 17 dB. If you achieve 17 dB difference, then you'll always hear it from one direction. Somewhere between gives you full image shift. So this 30-degree line is important to determine what we call stereo recording angle in microphone array recording. If you want to be very precise about your stereo imaging, how wide the whole stage should sound, and things like this, you need to understand the recording angle concept. So I'll demonstrate it when we come to the actual demo. So this is just an additional information I included only for those who are interested. But the results so far were obtained using the 60-degree speaker angle, right? So we always use this 60-degree triangle setup. But what if you increase the angle or decrease the angle between the speakers? Do we need a different psychoacoustic function? Yes, we do. That's what I found from some experiments. And basically, you need to scale the level difference and time differences to make it work for an arbitrary speaker angle. So basically, what this suggests is that for different loudspeaker base angle, you apply some correction factors. Because my data are based on the 60-degree base angle, the correction factor will be 1. So it's the multiplication factor. But if you use a larger speaker angle, you need to multiply the original time and level difference values with some coefficient. And this coefficient is basically determined by the ratio between your target speaker angle and your 30-degree speaker angle in terms of the resulting ITD, inter-oral time difference. So this is not the actual interchannel time difference, but it's inter-oral time difference that's caused by the specific speaker position. So if you have this relationship, then you can obtain the necessary coefficient. This is an engineering assumption I came up with, and then I applied this to some listening tests and then found these curves work pretty well. So I started using this relationship. That led me to this more global time and level trade-off functions. So instead of saying 30 degrees, 20 degrees, 10 degrees, this is basically the amount of image shift between any loudspeaker pair with any speaker angles. So for example, if you have 90-degree speaker pair for like quadraphonic reproduction, then you need to apply more level difference or more time difference. So for example, 1 millisecond is not going to be enough for you to perceive sound image at the fully panned position. So 1 millisecond was for the 60 degrees, then you need about 1.4 millisecond for 90 degrees. Or 17 dB is not going to be enough for 90 degrees. You need about 23 dB for that. Okay, so this is a global trade-off function that we're using in the latest version of MARRS. So at this point, I'll share my web browser just to show you how the MARRS app works. So this is the address marsweb.hot.ac.uk. If you go to this website, and this is introduction page. But yeah, if you I'm gonna wear headphones at this point. Yeah, there are two different modes, graph mode and stage mode, but we'll start with the stage mode here. So if you don't like these colors of the object, then you can just restart and it will give you some random color like this. Yeah, so as you see here, we have this stage and we have the config window here. And if you scroll your mouse over the stage, then you can zoom in and zoom out, right? And then the microphone array can be moved front to back, and your object or the object can also be moved around. And you can see the object here in this view follows, well, changes based on your actual physical position of the instrument. These are the perceived image positions. So that's basically based on the trade-off relationship I showed you before. So let's say, yeah, we have this XY 90 degree preset at the moment, and let's not worry about other things for now. Just I'll show you what happens when you move this source number 1 to at about minus 93 degrees to the left. Then you can see this, well, actually 97 degrees. Then you can see this image for this source will appear fully wide to the left. If you place it about 45 degrees, actually the number 2, this number, yeah, it will be localized somewhere around there. Actually, I read it in a sound recording textbook, and I was shocked actually, because it was the biggest lie. You know, when you actually have 90 degree XY, and the textbook was saying that you should aim to, well, basically angle this microphone so that it points directly towards the edge of the sound source. Then you will have a full sound like stereo width. Yeah. But you see what happens here. Number 2 and 3, they're gonna be very narrow in position. Yeah. So if your orchestra is this wide, for example, and then you place your microphone around there, it's gonna be very narrow as a result. So what you need to do is you need to place the microphone really close to the orchestra. Now you have fully wide positions. So let's assume this is our string quartet, and I want to place the microphone around there. I mean, this one grid is 1 meter, so 1, 2, 3, yeah, about 3 meters away. And then you can actually see the distance for each source: 2.74, 3.27. Yeah, and then you can see how much ICLD you achieve and ICTD. Because it's XY technique, you don't have any time difference. You're only using level difference. So 6 dB is never going to be enough for fully wide stereo image. You need to place microphone very close to the ensemble. Then you get the necessary 17 dB difference. Okay? Yeah, so this tool basically visualize this, and then I'll play the sound now. Hopefully you'll all be able to hear the binaural audio. I can also reduce the reverb completely. More reverb, no reverb. And then maybe I'll just mute. No, it's a solo the cello. It's not gonna be fully wide on your headphone because I'm simulating 60 degree loudspeaker playback. But if I turn it off, now it's just a stereo. Yeah, you probably hear it slightly outside your head. Yeah, that's good. Now, if I move away, yeah. But in recording, we have to think about direct to reverberant ratio first, because that will determine the clarity and you know the energy, the excitement of the music. If you place microphone too far away, then it's going to be too washy and too reverberant. If you place it too closely, then it's going to be just too direct. So usually recording engineers place microphones around 2 meters away from this, 1 meter or whatever. And then you can raise the microphones too. So on the side view, if you go to the side view, and then you can raise the microphone, and then you can see how this stereo image changes according to the height. And then you can also apply the tilting. So this pitch, you will point it more towards the source, right? So this is more like what we do in actual recording. Yeah, you can see this. Now I'll demonstrate how different techniques give you different sounds. So let's hear this. And this is just XY90, which is quite narrow sounding. Now let's try AB 50 centimeters. It's a pair of omnis spaced apart by 50. You hear that difference? Yeah, it's more spatial, but now you probably struggle to pinpoint where it is exactly. Bloom line, ORTF. It gives you very wide sound, as you can see here, right? And NOS, or something, Faulkner, pair of figure of 8, XY 180 degrees. So this back-to-back cardioid gives you full stereo width, because at that angle, the ICL is already 24 dB, so you can even make this ensemble slightly narrow too. At this given distance, your stereo image will still be wide enough. If you go with XY90, again, it's quite small. So ORTF, and then you can simulate the reverb. The preset is the same pulse figure of 8 pair placed about 8 meters away from the source. It's a reverberant concert hall. The picture I'll show you later. So if I mute. So it's like a pre-fader reverb feed. So as you go further away, the source level stays the same. Sorry, the reverb level stays the same, but only the source level goes down. You can decide what kind of balance you like. Yeah. And actually, you can load your own samples here. If you go upload, and then you can upload your own sound sources for each individual source. Source 1, source 2, source 4. And also, if you have an impulse response from a space, stereo impulse response, you can also load it there too. It's not just the same pulse, but yeah. So I'll briefly show you the graph mode. So this graph mode, depending on your configuration, you can see the localization curve, which shows the relationship between the actual source angle and the perceived image angle. And it changes depending on your configuration. And you can also see the amount of time and level difference. So at this particular angle, so when the source is at 60 degrees, you'll have a certain amount of level difference and this much amount of time difference. And it changes depending on the spacing, of course. More spacing gives you more time difference. It depends on other parameters. And you can also choose two different speaker base angles based on the algorithm I introduced. So 60 degrees, but if you can change to 90 degrees, yeah, it's just changes in the image position. Okay, so yeah, I suggest you play with it, and I'm sure it won't be difficult to understand what's going on here. Yeah, right. So that's the first half, and I'll move on to the second half. I'll introduce some recording techniques, microphone techniques, again based on this psychoacoustic model, but also on some other research findings. Sorry, let me just turn off my Slack because it makes noise. Right. So ESMA 3D is a microphone configuration I proposed a few years ago. It's called equal segment microphone array 3D. This general concept itself, it was actually developed by Michael Williams in the 80s, but the motivation wasn't for 360 VR. It was more for quadraphonic loudspeaker playback. But I thought that concept is really perfect for using, for being used for 360 VR, because with ambisonics you can rotate the sound field, you can capture the 360 scene. But I always didn't like ambisonics, especially for loudspeaker playback. I mean, technology advanced, and these days ambisonic can sound pretty good in binaural headphone playback, but still over loudspeakers you have this problem in coloration and very narrow sound width, and this phasey effect. It's known problem with ambisonics. So I came up with this ESMA 3D idea. Michael Williams originally proposed using about 23 centimeter spacing, but I've already told you about this dependency of image shift factor on loudspeaker base angle. So 23 centimeter works fine for 60-degree base angle, but if you use 90-degree base angle, you need larger spacing, because this angle, I mean, all these four cardioids should point towards 45 degrees angle orthogonally. So the only option you have is the spacing. If you want to get the localization correct, you need to increase the spacing. So I've done some experiments, listening test, and found that 50 centimeters, according to my model, actually works best. So I decided to make it 50 by 50 centimeters square of cardioid microphones. And then I add additional 4 cardioid or supercardioid microphones facing upwards to capture the height information for 3D sound capture. And this vertically constant but horizontally spaced concept is basically my own concept that was used for Schweppes ORLTF 3D microphone array. They actually took the finding from the paper and used it for ORLTF 3D. But this ESMA 3D is like an open configuration. Anybody can try. So the reasoning for the vertical constants, because we know that horizontally spacing matters, because as you heard, spaciousness improved with the spacing, but vertically the same thing doesn't apply, because our ears are horizontally spaced, not vertically spaced, right? So if you have the ears like vertically spaced, and then placing microphone higher up would make sense, because the time difference would matter. But our ears are just horizontally spaced, and these 2 points capture all the information from the ceiling and everywhere at the same point, right? So the same thing applies here. Horizontally, it needs to be spaced, but vertically, this 0 centimeter spacing actually produces more spatial impression sometimes, depending on the source. It actually widens the source width even more. Between 0.5 to 1.5 meter spacing, there is no difference. So there's really no reason to make the 3D microphone array really big, like cube. Of course, some engineers really prefer to use omni microphones and space the height channel like 1 meter or larger. Of course, that could be useful if you're recording a big sound source like organ or choir on the risers. The main thing to consider is whether you want to capture a direct sound for the high channels or not. If you just want to capture a lot of ambience for the high channels, it's best to avoid the direct sound in the high channels as much as possible, because that can cause unwanted image shift or comb filter effect because of the delays. If you got a lot of direct sound in the height and then combine that ear with the direct sound from the main channels, that causes a lot of comb filter effect in the ear signal. So depends on how you look at it. I mean, if you experiment with from random microphone configuration and find your own favorite settings, you know, for whatever the reason is, it's of course, you know, it's a combination of science and art. You need to actually find the point where you need to make the balance between the two. But from a purely psychoacoustic and scientific point of view, you can consider to separate this direct and indirect components as much as possible. And that gives you more headroom to play with the height channels in mixing. Because if you don't have direct sound in the upper layer, purely reverb, then you can always raise the level without increasing source loudness or causing image shift, or, you know. That was the motivation for this approach. So I've also found that you need to apply at least 10 dB, 9 to 10 dB reduction of the direct sound captured in the height channels. So if you manage to do that by using a cardioid microphone facing upwards or supercardioid facing upwards, then you can really effectively remove the direct sound, the crosstalk. And as I said again, this spacing really doesn't matter. I'm not saying that you shouldn't use spacing at all. If you need to, sometimes you have to, but large spacing wouldn't matter. I mean, maximum about 30 to 20 centimeters would be sufficient to create enough decorrelation you might want to capture. Because decorrelation vertically applied is not effective below 500 hertz. That also means you don't need much spacing. So that brought this design concept, 50 by 50 square. Within this Rycote Cyclone windshield, you can use this vertically oriented XY configuration. So cardioid for the main and then supercardioid for the height. And some subjective evaluations showed that this array sounded much more spatial, more externalized and wider compared to the first order ambisonics. And different decoding like Maxari and mode matching decodings, they all sounded lower than the ESMA 50 centimeters. And as you also can see that ESMA 50 sounds closer to the reference dummy head recording. It sounds more like a real life situation in headphones. And not to mention that this sounds much more natural and you can have a wider listening area over speaker playback. You can walk around and you wouldn't hear any strange phase effect at all. It's very natural and wide. Whereas the ambisonic, you have to sit down at the sweet spot all the time. So depending on your applications, this microarray could be useful. So for more details, you can read these papers. And so I played some sound. This is binaurally rendered ESMA 3D recordings. 2 years ago, I think it was already 2 years. Yeah, 1.5 years ago, 2019 AES convention in New York. I brought my ESMA 3D rig with me, and me and my research assistant were wandering around in Manhattan and you know, set up this microarray in 2 minutes and just sneak to record some sounds from this famous place, and we were kicked out in 5 minutes. The security guards came along and you can't record in this place, and no professional equipment, no camera, of course. Well, we're just begging these guys, can we just record it 2 minutes and then we'll go away? And so yeah, that's how we captured this sound, and let's have a listen.
Attention customers, for your safety and the safety of others, please do not sit on the floor or stairs in Grand Central Terminal. Thank you for your cooperation.
And this is going to be loud. It's a construction site, this street. And this is in front of the Penn Station. And this is my favorite. It was under the Manhattan Bridge, because we captured this train running on the bridge, and the microphone array was, I don't know how far it was, about 20 meters, 30 meters below the bridge. Yeah, so hopefully you'll hear some elevation of the train noise. Okay, so one more. This is 8-channel version of ESMA. So before I only showed the 4-channel ESMA with 4 height microphones, but this is 8 microphones in a circle with 4 height microphones, and I captured this performance in York Minster in York in England. It's only an hour away from where I live, and the Igbo singers, they're very good singers, performing in this very reverberant space. And then I'll let you guess how long the reverb time in this place is after you listen to it.
Six seconds.
6 seconds. Could be. Did you enjoy it?
Wow, man.
Yes.
Great. It sounds really like enveloping, doesn't it? It sounds like, yeah, very immersive. I mean, it sounds even better with actual speaker playback, you know. We are listening to it using generalized HLTF. But yeah, basically the reverb in this place is amazing. It's very large. I think I didn't measure it myself really, but I think it's as long as 10 seconds. Yeah. But the tricky thing about recording in this kind of reverberant space is because if you place microphones too far, then you may end up very, very reverberant, very like unclear, unintelligible sound. But guess where the microphone was? I mean, it's in the middle, and each singer was about 4 meters away. 4 meters in this kind of space could be regarded as too far. You know, I didn't use any spot microphones here. I just used the main microphone array in the middle. Each singer was about 4 meters away, which is pretty long distance in this kind of reverberant space. But I don't think it sounds too reverberant. It sounds natural and intelligible enough. That's partly because the layout was circular. So I experimented two different layouts with the circular layout and all the singers in an arc in front, and you only get reverb from the back. So that second scenario made it sound too reverberant. The sources in the singers in the front sounded too distant, too muddy, too reverberant, because everywhere else you just hear reverb. But in this case, you're surrounded by the singers. You hear direct sound from all directions, and they basically mask the reverb slightly more effectively. So you have totally different the perceived direct to indirect sound balance. You're probably hearing my daughter crying outside.
Don't worry. You probably hear mine. So
basically source and background sound. Yeah, perfect timing. So yeah, that is the big finding I actually found in this recording session. And then I actually really like this circular layout with ESMA 3D in the middle. And I don't like spot mics sounds personally in this kind of a classical recording setup. I don't tend to use spot mics much. I place them sometimes, but I just don't use them much in the actual final mixing. Because if you start mixing main mics with spot mics, you start having this coloration and the delay matching. It becomes an issue. Then you need to choose either the spot mics or the main mic. And then I always go with the main because, you know, I know my balance, the where to place the microphones. If I choose to use spot mics, then I'll just capture the ambience only in the space and then just add the ambience later on. So, yeah. But different people have got different approaches. So just to finish off, I'll just introduce this database. Some of you may already have found this, but this is a 3D Marco open access database I created 2 years ago, supported by DPA, Merging, and Genelec. So we basically used 71 microphones simultaneously, 53 of which were DPAs. We used like, I don't know how many, 9 different 3D microphone configurations, placed all at the same positions. And this is the concert hall that I used for MARRS at the reverb that you heard. So yeah, these are the microphone arrays we included, all of them. Including Eigenmic, the high-order Misonic Eigenmic, as well as KU100, and some supporting microphones for 22.2. So it's a massive database, and you can also have these impulse responses captured at these positions. So you can create your own virtual 3D recording. You just have to convolve dry signals with these impulse responses, and you have all different microphone arrays. Yeah, some session photos. We had a string quartet, the organ, and piano, solo, singers, single sources. So you can visit this website and download the database from there. And I also included a repo template. So you just open the repo template and then it will have all the recordings organized for you. Yeah. And you can also binaurally listen to them if you're using something like IEM binaural renderer in Ambisonics. This is a very recent paper, just published about a week ago. It's a multi-channel microphone array review paper in JAS. It's open access, so you can freely download it, and it's got all the descriptions of existing 3D arrays and some discussions at the end.